And today what I want to do is going to talk about Fourier series and transforms. And this is the last of, I think this is the last of the major topics we're going to cover in the first half of the course. Also, in addition to this, we're also going to cover next week some stuff on complex variables, I think. Yeah. So this is one of these topics where it's something you guys should have seen, and it's also something you use a lot in physics and engineering specifically, where it kind of goes beyond some of the math that non-technical people would have had. And and as I get into this, I mean, it becomes very clear where this is useful at. And this is one of these things that I use a lot in my research, and mostly because there's applications to doing to Fourier transforms. Like if you're trying to do computational physics, then you can actually use your Fourier transforms not just in the data analysis side, but also just for calculating derivatives that make things work out a lot better. So let's get started. So the first half of this, I'm going to talk about Fourier series. Fourier series. And the second half, I'm going to talk about Fourier transforms. So my plan is basically I'll go through the Fourier series stuff, and then we'll take a break, and then we'll get into Fourier transforms. And so the basic idea is that if you have some function, let's say a function of theta, where theta exists from 0 to 2 pi, then this you could say is a periodic function, meaning that you have the same answer at 0 as you have at 2 pi. So if you imagine like a sphere, then as you go along the equator of the sphere, you come back to the same point all the time. So what happens is that you could say that your function, since it's periodic, can be the sum of every periodic function possible. And this kind of goes back to what we talked about with differential equations, where the solution to your differential equation is every possible solution to that differential equation. And here, the solution to a periodic function is the sum of every possible periodic function. And so every possible periodic function from 0 to 2 pi is going to be equal to taking a constant, in this case it's divided by 2. Some texts they don't divide it by 2. And then adding to that the sum from n equals 1 to infinity of a sub n cosine of n theta plus b sub n sine of n theta. Okay? And so this is basically the sum of every possible periodic function. And the reason why this works is because a sub n and b sub n, these are just coefficients. They could be 0, they could be imaginary, we don't know what they are. But cosine, of course, is periodic. And when you put in the n, what happens is if n goes from 1 to infinity, then it's basically saying if you just have n equals 1, then obviously you get the same answer as 0 and 2 pi. If you have n equal to 2, then you get to go 2 cycles between 0 and 2 pi. And so that represents like a higher frequency. And the same thing for sine. But the thing is that if you have n equals 0, then the sine function disappears, and the cosine is just going to be 1, so that's where your constant comes in. So you could almost as easily say this is the sum from n equals 0 to infinity, and it works. But the basic idea is that if you can find out what these coefficients are, then you can take your periodic function and represent it as an infinite series of periodic functions, which are sines and cosines.
So is your A naught divided by 2 because you're eating across the cosine and sine because you're adding?
Well, it's technically the n equals 0 would be 0 for the sine.
Okay.
But I think the reason why they say divided by 2 is because when it comes time to find the component, it's a little bit easier to say it's divided by 2, and then you don't have to divide by a 2 later on. So basically, the whole trick in Fourier series is just figuring out what these coefficients are, or if you're given the coefficients, to figure out what it sums to. So in this sense, this relates directly not only to the differential equation stuff, because like a differential equation is the sum of all the possible solutions, but it also relates to your your infinite series, because this is an infinite series. Okay. So, you know, and then soon enough, this is going to relate to the stuff we talked about with integration. So we're just capturing everything. So the idea here is that if you take, for example, this f of theta, okay, and let's say you integrate this with cosine of m theta, d theta, and you sum over m from m equals 1 to infinity, and this all goes from 0 to 2 pi because that's the domain of periodicity. Well, if you sum over this f of theta, which supposedly we know, that would be the same as summing over each one of these components on the right-hand side. So that's like summing, so it's like you integrate the sum from m equals 1 to infinity of the integral from 0 to 2 pi of a naught over 2 cosine m theta d theta, plus the same thing where now we're summing over both m and n of integral from 0 to 2 pi of a sub n cosine n theta cosine m theta d theta. And then you're doing the same thing with the sine term.
So you just multiply everything by cosine m theta?
Multiply everything by cosine m theta, and then sum it over, and then integrate. Oh, sorry, not to infinity. My bad. This should just be the 2 pi. So for everything, you're basically just you're integrating. You're multiplying by the cosine m theta. You're integrating from 0 to 2 pi, and you're summing over all the different possible values of m. Okay?
It's m plus or minus 1. Sorry, and then the last.
Oh, sorry, it's m equals 1.
Oh, m equals, okay.
Yeah, so I'm saying m and n equals 1 to infinity. Okay? So what happens with this first integral? This is easy, right? Anybody know the solution to that one? 0. Because you're integrating cosine from 0 to 2 pi is the same value as 0 and 2 pi, so then this must be 0. For the second term, what happens if n and m are not the same, then this is going to give you 0. And let me show you how that works. So basically, if you integrate from 0 to 2 pi, cosine squared of, say, n theta. That's n and m are the same, d theta. Then this is going to give you theta over 2 plus sine of 2n theta over 4n integrated from 0 to 2 pi, which is equal to pi, right? And this comes out of your handbook, the formulas, the tables, and you can also just kind of integrate this by just understanding how, just having a cosine squared.
You said that's equal,
That's if n and m are equal. So this is basically for m equals n. Okay? For m not equal to n, then now you have the integral from 0 to 2 pi of cosine n theta, cosine m theta, d theta, right? And so if you have cosine n theta times cosine m theta, what happens? I mean, keep in mind n and m are both integers. Anybody remember? You end up getting a sum of angles, right? The sums and differences. Does anybody remember the formula for, yeah.
Cosine squared of theta cosine.
What? Yeah. Well, it's kind of like, yeah, cosine. Like if you have cosine alpha, cosine beta, I think it's minus sine alpha, sine beta.
That's equal to cosine alpha plus beta.
Yeah, then it's is equal to cosine alpha plus beta, and then what you can happen is you have effectively then. See, there was another term I'm missing. But the basic idea, yep. No, I have to. I didn't bring my handbook, so I can't remember exactly what the formula was.
So that's all that is by doing it stated in parts, where you do intervals by parts, parts, and then by the second term down, or third term down, you have to do the same thing you started with,
right?
Plus something, and so you can do some algebra.
Exactly. So, but the idea though is if you do this, then you're basically going to end up with something here, which is just like integrating cosine theta from 0 to 2 pi, and it's periodic. So it's going to give you the same answer at the end.
Can you just say that cosine alpha, cosine beta is equal to cosine alpha plus beta plus the sine terms, so the sine terms will go away?
Yeah. The sine?
There's no n in front of them, so they are the same angle.
No. It's different. So you end up with let's see, this would be like 0 to 2 pi of cosine of n plus m theta, and then this would be plus sine n theta cosine m theta. And I can't remember how the addition of those angles work out, but the first integral is going to go to 0, right? Because these are two integers and this is periodic. The second one, n and m are still different.
So it's supposed to be sine, like a sine cross.
Oh yeah, sorry, you're right. It should be sine. Sorry. Sine m, sine. Yeah.
Alpha C1 and theta, cosine A, cosine B equals 1/2 cosine A minus P plus cosine A plus P.
That sounds.
You get that, you can do it, I guess.
Yeah.
That should be 0. I do.
Yeah. So it was like cosine A times cosine B equals cosine 1/2.
Then cosine A minus B minus cosine.
Oh yeah, thank you. So it gets rid of the sine term. Yeah. So it's cosine alpha cosine beta equals 1/2 cosine alpha plus beta times minus, is it minus or plus?
Plus.
Thank you, plus cosine alpha minus beta. That's what I was looking for. So if you look at that, then you're basically going to end up with you're basically going to end up just kind of with the equivalent of just having cosine of these two integers. And so let me fix that down here. So this would be cosine n minus m theta, and we put a factor of a half in front. So when you integrate that, this is an integer, this is an integer, so you get 0, so the result is 0. So that means that if n and m are not the same, this integral is going to come out to be 0, right?
Some sort of like trying to picture like how the graphs are summing up to be 0. Is that like some sort of orthogonality, like property of the cosine graphs, like when they shift over?
That's a good question. Remember, when you integrate, you're integrating the area underneath the curve, right?
Yeah.
So the way you can think about it is, if you have two different cosine functions, and you're integrating it over the entire series, and let's say you have one of these is n equals 1 and the other is m equals 2. Okay, so one of them is twice the frequency of the element. Then what we could do is we can actually draw that. And let's say this is going from 0 to 2 pi. Okay, so here's your cosine function. I'm trying to be as accurate as possible, but this is not art class, so keep that in mind, please. This one is your n equals 1, right? And then your n equals 2 is going to basically be twice the frequency. So it's going to go from here to here, so it's going to go like this. I think it go like this, right? And so I guess the idea is that when you integrate it, you're looking at the area under the curve. And so what happens is if you multiply these two together, and that's the trick, they're multiplied together, then you have to imagine that here, for example, this is going to be negative to here, and then these two are opposites. And so when you multiply everything together, that's how you can see it kind of cancels out to 0. But for me, it's easier to see it from when you're trying to take the sums, because then you could see that when you're summing the two angles, and then you're trying to take the difference of them, you can see that that has to integrate. All right, so that's why it is that for this one, you have that n must be equal to m, otherwise this is 0. Now for the last interval, you have a sine and a cosine. And so what happens is you can have the integral from 0 to 2 pi of sine of n theta, cosine of m theta, d theta. And then what happens is, even if you have n and m equal to each other, this is still going to come out as 0. Because if you have, let's say you have n equal to m, so this is, then this will imply that you have the integral of from 0 to infinity of sine of n theta, cosine of n theta, d theta, which is equal to sine squared n theta over 2n, evaluate it from 0 to 2 pi, and since sine of n theta is periodic, sine squared of n theta is periodic, and that's going to give you 0. So that, even if n and m are the same, that's going to give you 0. If n and m are different, then you still basically have these two periodic functions and you're multiplying them together, then you're still going to end up getting something that's going to be periodic. And you can do that whole thing like we did up here, but instead of this cosine times cosine, you're going to have like sine alpha cosine beta, and I think it leads to something very similar to what we had here, where I think it's like this is sine of alpha plus beta, I think minus sine of alpha minus beta times 1/2.
It's a plus, but I think back to that.
It's plus? Okay, thanks. So you basically end up with the exact same argument here, where if n and m are different, then this is still going to be 0, because when you integrate it, you're just integrating the sign. If n and m are the same, then the second term is 0, and the first one still goes to 0 for the same reason. So what you get out of that is then this last term must be 0. So what happens is you end up with this integral, which comes out to pi, right? So therefore, we have that the integral, if you take this sum from m equals 1 to infinity of f of the integral from 0 to 2 pi of f of theta cosine of m theta d theta, that is equal to effectively the sum from n equal n. Well, I'm just going to call it m, because well, I could say m and n equals 1 to infinity, and integral from 0 to 2 pi, and I'll put in a delta function n m, which basically says n and m have to be equal to each other. And then I have a n cosine of n theta cosine of m theta d theta. Okay? Now, this says that n and m have to be equal. So it's the same thing as just having cosine squared. But now we know that the integral here is going to give us pi, and n and m have to be equal to each other. So now we just have the integral, we just have a sub n times pi, right, is equal to that. And so therefore, this implies that a sub n must be equal to 1 over pi times the sum from m equals 1 to infinity, or sum over n. Sorry, we lose the summation. We don't need the summation. Sorry, back up a second. We lose the summation when we did the when we evaluated the delta function. So forget that part. So what we have left is the integral from 0 to 2 pi of f of theta cosine of n theta d theta. In other words, all I had to do was take my initial function and multiply it by cosine of n theta and integrate that from 0 to 2 pi and divide by pi, and all of a sudden one of my coefficients just pops out. And because, you know, I could essentially recover my A naught from this by just simply taking n equal to 0 and integrating it. And that works too. Now, for the next thing, we could actually recover the B in pretty much the exact same way, doing the same math by just taking a sine instead of a cosine. So basically what this means is we take any periodic function, and from that periodic function we can find the coefficients in order to make our Fourier series. And since sine and cosine both oscillate, they're both oscillate around 0, all this coefficient A naught does here is basically give you the mean value. So it's the number that you're oscillating around with respect to. So if you plotted this function, you just kind of look at how this thing goes through 0, and that's the mean value of it, and that's what you get.
In case you always just say it's 0.
Not always. There's going to be some problems where it's not going to be 0. And so what this does is that basically if your function, let's say your function looks like this is 0, okay? And so let's suppose we had a function, and this is 2 pi, and it's periodic like this. Well, this value right here is essentially your 2A naught. So that's what it's going around. And that's all it does is just shift things. And you're going to run into problems like, for example, you might have something like this. This is periodic, right? And to really look at it as periodic, you got to keep in mind that the mean value is like right here instead of at 0. So the reason why I spent so much time on this part, and a lot of their other stuff with the lecture today goes much faster, is because this whole concept that we can get these coefficients from doing these integrals is going to come up later on in the semester when we start talking about eigenvalues and eigensolutions and orthogonal functions and things like that. So it's kind of like something I'm just kind of foreshadowing. We're going to see this whole thing again, but in a very different light in the future. So, yeah.
Once you have the delta, will be the integral to x again.
Oh, right here, the delta?
Right.
Yeah, the reason why I put that in there is that the delta basically says that if n is equal to m, then you got 1. If n is not equal to m, you got 0. So it's just basically a way of putting a logic statement inside of your equation. And I'm trying to be as precise as possible for when you guys refer back to this later on. I mean, I don't think my notes are quite as precise as what I'm saying here. So that's why I want to be very clear. Okay, now, one thing I do want to note is that if you have, depending on the symmetry of your function, you can then kind of take some shortcuts with this, because depending on your symmetry is going to determine whether or not you need both A sub n and B sub n or just one of them, and what they're going to look like. So for example, if you have an even function, an even function is basically a function where it looks the same on both sides of 0. So if you take theta equals 0 and you look at each side of it like a mirror, the negative and the positive sides, then it looks like you're going to have b sub n all equal to 0 because it's going to be represented by cosine functions. Cosines are even because cosines are same about each side of 0. If it's an odd function, that's the opposite. An odd function basically says a sub n's are all going to be equal to 0 because you're going to have something that's anti-symmetric about the 0. So this is an even function, and this would be an odd function. Okay. Now, if it's an even function, that mathematically that looks like saying that f of theta is equal to f of minus theta. And an odd function is f of theta with a negative sign is equal to f of minus theta. And that's the exact same symmetry that you see from sines and cosine functions. So this is only cosine. This is only sine. All right? Now, what if you have an even function, but it's symmetric about 1/2? Or about pi over 2. And what that looks like is, let's suppose you have a function like this, and it's symmetric, right? But then this is pi over 2. And when it kind of dips down and comes back, so that when it hits a minimum at pi over 2. Let me draw that a little bit better. Okay. So what I mean here is, I'm going to say this is pi over 4. And then this is pi over 2. Okay? So let's say your function is symmetric. It goes like this, hits the minimum, and then comes back up. And then meanwhile, on the other side, it does essentially the exact same thing. Okay? Well, when it does that, it's not only symmetric, but it fits into a very specific form of symmetric. And you could say that your f of pi over 2 plus theta is equal to your f of pi over 2 minus theta. And so, of course, since it's even, it's going to be only cosine. But you're only going to have only even cosine functions. So you're going to have all the odd values of your cosine expansion terms are going to be 0, and all of your b values where the sine functions are going to be 0. This is so only cosines with even n. And so it's kind of weird. You see something like that, but it's almost like, you know, all of your odd value frequency terms are going to just sort of disappear because they won't give you that symmetry about pi over 2. And so it's almost like when you're doing your Fourier series, you can just ignore all the other terms that don't quite fit that criteria. So if I give you a graph and you see that it's clearly an odd function, like I give you a graph and it looks sort of like this, then this is an odd function, right? And if it's an odd function, then there's no reason you have to do this integral for both the cosine and the sine. You can just do it for the sine, and you're done. So all you have to do is find all the b sub n's, and you're done. But if you look at it as it's an even function, and all you have to do is do it for the cosine functions. All right. All right, so let's do a little example here. I have a function, f of theta is equal to either +1 or -1. And it's +1 if you have if your theta goes from 0 to pi, and it's -1 if your theta goes from pi to 2 pi. And so if you graph this, then what happens is you have something that looks like this. Okay. Now, first off, when we look at this, you can see that this is an odd function, right? Because it's anti-symmetric about 0. So we know it's odd. And also, because it's odd, that means there's no cosine terms. So all of the a sub n equals 0. Now also you'll notice that this right here is pi over 2. Because pi over 2, or sorry, that's 3 pi over 2. That's 3 pi over 2. This will be pi over 2 right here. So it's symmetric about pi over 2, right? Yeah. So since it's symmetric about pi over 2, and that means there's going to be no even sign terms. It's kind of the opposite rule as the cosine thing. So what that means is you're only going to have all of the b sub n 2n plus 1, which are going to be non-zero. So you're going to have something like your b sub n coefficient is going to come from 1 over pi times your integral from 0 to 2 pi of f of theta sine of n theta d theta. Okay? This is just the generic formula. Now what happens is we know because of the symmetries involved here that all we really got to do is integrate from 0 to pi over 2. With the idea that the sine function here is going to kind of take care of the symmetry. And so if we only integrate from 0 to pi over 2, all we have to do is multiply that by 4, and we're going to get the whole range. This is kind of using symmetry here. So we say 4 over pi times the integral from 0 to pi over 2 of f of theta of sine of n theta d theta. In other words, if we know something is symmetric about a certain point, all we have to do is integrate up to that point of which it's symmetric about. And in this case, that's just simply the pi over 2. Now we know that if you go from 0 to pi over 2, the answer is just 1, right? So all we're really doing here is integrating now for over pi, integral from 0 to pi over 2 of sine of n theta d theta. Okay? Because it's f of theta is just equal to 1 in that range. So now the integral of sine is just going to be, what, negative cosine? So we have, this is equal to negative 4 over pi. What?
N pi.
Oh, sorry. 1 over n cosine n theta, evaluated from 0 to pi over 2. And then what happens is this is going to give you at pi over 2, or let's say n is equal to 1 for a second. Cosine of theta at pi over 2 is equal to 0, right? And since n is odd, that also applies the same as 3 pi over 2 and 5 pi over 2 and so on. So the reason why we chose the pi over 2 here, part of the reason is because it gives us a predictable answer here. Meanwhile, cosine of 0 is going to be equal to 1. No matter what number we multiply it by, it's still going to be cosine of 0. So what happens is this is going to give us 4 over n pi is our integral. So we just basically just use the heck out of the symmetry. So the coefficient is just going to be 4 over n pi. And so now all we have to do is we just say, well, that means that our function, f of theta, is equal to 4 over pi times the sine of theta plus sine of 3 theta over 3 plus sine of 5 theta over 5, etc. And that's our series. Now, if you look in the book on page 98, this is what you see here is basically they took this exact same function that I had and they just start filling it in. First they put in the first sine wave, which kind of looked like this. And then they kept adding to it, and eventually they got something that looks kind of like this. We got very blocky. You know, kind of like if you ever seen use an oscilloscope and you see this nice square pattern. That essentially comes from just adding up all these frequencies over and over and over again. And so eventually you can kind of come to this pattern. And that's on figure 4.4 in the book. So what happens then is, let's suppose we take theta equal to pi over 2. Then f of pi over 2 is equal to plus 1, right? Well, that means that 1 is equal to 4 over pi times the sine of pi over 2, which is equal to 1, right? And then the sine of 3 pi over 2, which would be the sine of 3 pi over 2 is equal to minus 1. And so that would be minus a third. That's minus 1/3. And then 5 pi over 2 is plus 1/5. And you have minus 1/7, etc. Right? Well, let's multiply this through, and we get that pi over 4 is just equal to 1 minus 1/3 plus 1/5 minus 1/7, etc. This is known as Gregory's series. So basically, you can create this infinite series where it can actually give you what pi is by just simply calculating here from the Fourier series.
If you rearrange terms, though.
You can't. No. But it is interesting. And so the nice thing here, just multiply the fourth or you can get pi. Yeah, really, really handy. Yeah. Now another example, and so we have a couple more things, and then we'll get to the break. Next thing is, let's suppose we have f of theta is equal to cosine of k theta. And theta, of course, exists from minus pi to pi. Well, k is not an integer. Or let's say k is not necessarily an integer, okay? If this was an integer, this would be like the easiest Fourier series in all of history. But can't quite do that. This is going to be very similar to something we mentioned in Bernoulli numbers. Now, first off, I don't even think I have to ask if this thing is even or odd, because obviously it's an even function because it's just made up of cosines. So your a sub n is equal to pi, 2 over pi times the integral from 0 to pi. We're using the symmetry about 0. So instead of integrating from 0 to 2 pi or from minus pi to pi, and then and having a 1, we just integrate half of that and multiply by 2. And then you have your f of theta, which is your cosine of k theta, and then you have a cosine of n theta d theta. Well, if k is not an integer, then the solution for this is equal to minus 1 to the n of 2k sine of k pi over pi k squared minus n squared. So obviously, if k was equal to an integer, you'd have a totally different answer here. And so what this is saying then, therefore, is that cosine of k theta is equal to 2k sine of k pi, which would be trivial if it was an integer, times phi, and then in the denominator, we're going to have each of the different values of n going from n equals 1 all the way up to n equals infinity, or n equals 0 to infinity. So now we can have 1 over 2k squared minus cosine theta over k squared minus 1 plus cosine 2 theta over k squared minus 4, etc. And so if you set k equal to an integer, so let's say k becomes an integer, then a neat thing happens, because here cosine of k theta would just give you, let's see, if k is an integer, then then this first term becomes 0, right? Because sine of an integer pi is equal to 0. And then you have 1 over 2k squared minus cosine of theta over k squared minus 1, and then all these other terms, and eventually you're going to get up to a term where it's going to give you cosine of k theta over 0, because you're going to have the integer that k is going to be equal, squared is going to be equal to whatever your n squared is. And when that happens, you get a 0 in the denominator. Now 0 divided by 0 is 1, so therefore this becomes cosine of k theta. And the reason why you get that as going to 1 is because apparently the sign goes to 0 at the same rate that the term in the denominator goes to 0. Because you're going to get effectively as this sign, from small angle approximation, sine of k theta, if you get it small enough, is going to basically become just k theta, or k pi, and you're going to have essentially a k squared term here, and you're going to have like a k squared term in the denominator, so they cancel out, and everything works out fine. So you can kind of prove that this is itself, which I don't know how useful that is, but at least it's something that shows we're consistent. You can also generalize a series to be periodic, where we might take, for example, let's say you have the length L, which is sort of the period of your system. Then you can define X to be theta L over 2 pi. And then when you do that, you eliminate theta and you now have X. And this is what we frequently use, where you just rewrite your Fourier series, but instead of using theta, you're using X. And you'll see things kind of written like this. And then you can recover your coefficients now, where you're dividing by 2 over L instead of 1 over pi. And you integrate from 0 to L instead of integrating from 0 to 2 pi. Your f of x cosine 2 pi and x over L dx. And then you do the same thing with your sine terms. So your symmetry and everything still hold. It's just that you're changing your variable so that you can work with something that's more convenient over how this thing is periodic. Okay? All right. Now the last thing is that you can actually do sort of a complex form. And this is useful if, let's say, the sines and cosines are useful if you know the symmetry of your function, but sometimes your function is neither periodic, or it's periodic, but it's neither even or odd. So it doesn't have a clear symmetry about 0. In which case you can basically take your f of theta and write it as the sum from n equals minus infinity to infinity of a sub n e to the I n theta. And of course, these e to the I n theta can become a sine and a cosine, or cosine plus I sine. And then your coefficients, which are all bogged down in your a sub n's, they can be imaginary, right? So they can actually take the place of making it into real sines and cosines. So it's sort of a catch-all. If you don't know your symmetry, or if you don't understand the symmetry, you can use this. And so what happens is you can also write this in terms of your x. the 2 pi I and x over L. And you can do things with this, like if you take your exponential term and you multiply it by its complex conjugate, then if I take those and multiply them together, and let's say I integrate it from 0 to L, the result of that is going to come out as going to be L delta ML, or MN. And the reason why is because within this exponential term, you could see that you can combine the exponentials, and literally you just end up with M minus N in the exponential. And if M minus N is equal to 0, then you get something where there's going to be a difference at the boundaries. If they're the same, then then you just get something that oscillates and gives you 0 when you integrate it over the boundaries. And so what happens is that you can define your coefficients as just being equal to 1 over L times the integral from 0 to L of f of x e to the minus 2 pi I in x over L dx. So this looks a lot simpler than what we were dealing with before, because you can just simply, all you have to do is just simply integrate it with the exponential term and you're done. And there's only one coefficient you have to find, as opposed to before where you have to find the ones for sine and the ones for cosine. So what this means is that if you know your symmetry and you have a clear symmetry, then you could just do the sine and cosine. But if you don't, then you can just use the exponential. And this also captures n equals 0 in here, so it gives you that constant term as well. Oh, well, the reason why you do that is because, remember, you're trying to recover your coefficient. So if you're integrating both sides, then that gets rid of this term. Okay? And so also I should note that if you take 1 over L times the integral from 0 to L of f of x squared dx, this is equal to 1 over L integral from 0 to L of dx times the sum over n of a n e to the 2 pi I n x over L. And because that's just f of x. And then we do the same thing, but we sum over m with the complex conjugate of that. 2 pi I m x over L with a minus sign. Then what happens is, when you do this, you're going to end up with your delta function here, because you're going to be integrating the exponential terms like I had up here. And so you're going to end up with the 1 over L. From the integral, you're going to end up with L delta mn. And then from the coefficients, you're going to end up with a sum. Well, actually, sorry, all this is under the sum over m and n. So then you're going to end up with just this, the coefficients multiplied by each other. So that's going to give you the a sub n and the a complex conjugate m. And so what happens is the L's cancel out. You resolve the delta function by saying m is equal to n, and you end up with just the sum over n of a n squared. And what this means if you get rid of all this junk in between, is that if you take the magnitude of f of x and you integrate it over all different range of x, okay, and divide by L, then the result is the same as if you just sum up all of the coefficients, you know, that coefficient squared. Or another way to put this is, if you think of x representing position, okay, and you think of n representing all the different frequencies, then what you can do is you can integrate, you know, or time. Then you can integrate something over the entire length of it, or you can integrate it over all the time that something's happening, and you'll get the same result if you just add up all the frequencies. And so what this tells us in physics is that we can actually tell something about a system by just simply looking at all the frequencies and adding those up, as opposed to looking at integrating over the entire space physically. It's a different way of approaching the physical system. And doing it the first way may not be practical, so the second way gives us the same result. Okay. All right, any questions right now over first step we did? Okay. All right, so what we're going to do, we're going to take a break, say 10-minute break, and when you guys get back, we're going to talk about Fourier Transforms, which is where some of the really useful stuff comes in. All right, so right now, we already talked about Fourier series. Now we're going to get into Fourier transforms. So the idea here is that we start off with our Fourier series. And I'm going to use the exponential series because that's the simplest thing. And we're summing over n of the coefficients e to the 2 pi I m n x over L. And we get our coefficients a sub n equals 1 over L integral from, let's say, minus L over 2 to L over 2, f of x e to the minus 2 pi I and x over L dx. All right, so basically, from what I said before, is that you can roughly consider this f of x to represent your function as a function of position or time. You know, think of x to be time, in which case the n, in a rough way, approximates your function as a function of frequency. So you can think of it as, this is basically saying, is the analog. You know, if you think about it like a record player playing music, you can think of it as like, this is basically looking at your, the music that comes out in terms of, you know, very basically what's happening and what the wave looks like. And this is kind of like the MP3 version of it, where it has it broken up into frequencies, and it as it's looking at each of the different frequencies as an individual thing, and then throwing them all together to make your music. So they're basically the same thing, but you know, people argue that there's a difference. They can tell the difference. I don't know, but you know, same thing in different ways. So what we want to do is we want to kind of elevate this kind of frequency thing to be the same level and the same kind of analytic function that we have with the position space. So in other words, this is an analytic function. This is like a discrete thing, which is a sum of a bunch of stuff, and together they're equivalent. So what we're going to do is we're going to take the case where L goes to infinity. In other words, when L goes to infinity, you are basically saying that your period or periodicity could go out to infinity. It may not repeat, okay? Which is kind of weird. You think this is supposed to be periodic, but saying that you're periodic over a period of infinity. Then, when you do that, what happens is you can define a new variable, y, which is going to be equal to 2 pi n over L, and g of y, which is going to be defined as L times a sub n. And so what happens here is that when you say L goes to infinity, then your sum ends up becoming an integral, because if L goes to infinity and n goes to infinity, then to cover this whole periodic thing, you're going to have an infinite number of points in between, infinite number of frequencies. So what happens now is we can say that f sub n, or actually I should mix upper and lowercase n, so sorry. If we take f of n, now we're going to sum from n equals minus infinity to infinity, and this is just some function which is indexed by n. We can say that, well, if this sum becomes an integral, then we can rewrite it as the integral from minus infinity to infinity of f sub n dn. Now we're integrating over all the values of n. And then since we can relate n to y, we can kind of replace our n with a y. And we could say that, well, this is equal to L over 2 pi times the integral from minus infinity to infinity of f of y dy. And so we've magically made our sum turn into an integral, and we've done it for some arbitrary function, or some function that's parameterized by n. So what we can do then is we can take our f of x, and we can write it as 1 over 2 pi times the integral from minus infinity to infinity of L a sub n e to 2 pi I n x over L dy. And that's basically taking this integral up here, or this summation up here, and going through the same process and turning it into an integral. Where you could see if you do the exact same thing, you're not touching the exponential term, you're not touching the a to the n term, but you're adding in the dy, and you're multiplying in the L over 2 pi. So now, since L times a sub n is equal to g of y, then this is just equal to 1 over 2 pi, since the integral from minus infinity to infinity of g of y, then the exponential term, dy. And then you'll notice here that y is equal to 2 pi n over L, so I can eliminate the 2 pi n over L and turn this into 1 over 2 pi times the integral from minus infinity to infinity of g of y e to the minus I xy dy. Okay? And then likewise, we can take our g of y minus ixy. Oh, oh, sorry, it should just be ixy. That's my bad. Just looking at the wrong part of my notes. So the g of y is just simply equal to L a sub n, and the L a sub n comes from this integral. So that's equal to the integral from minus L over 2 to L over 2. We multiply through by the L. And then we have f of x e to the minus 2 pi I n x over L dx. And so you'll notice here that first off, L goes to infinity, so we have this from minus infinity to infinity. And then you have your f of x, which is still there. And then your exponential term just turns into minus I xy dx. So this is cool now because we got a certain symmetry going between the f of x and the g of y. They're both analytic functions, and it's just that one is a function of x and the other is a function of y. And they both have this exponential term where one is just the inverse of the other. And the only difference between them is you have this 1 over 2 pi. And what you can do, if you wanted to, is you can actually take the 1 over 2 pi and divide it between the two of these. So you have a 1 over square root of 2 pi and a 1 over square root of 2 pi. So what happens is you call this a Fourier transform and an inverse transform. So you basically say, well, this is the Fourier transform of f of x, and this is the inverse transform. Okay. So what happens then is you can actually take the two expressions, you can combine them together, and you can have f of x is equal to 1 over 2 pi times the integral from minus infinity to infinity of, with respect to y, of e to the I xy of g of y, which is really equal to the integral from minus infinity to infinity of f of x prime e to the minus I x prime y dx prime. And what happens is you can rearrange the terms here. So you have, I'm going to take the x prime integral and move it out front. And so I have the integral from minus infinity to infinity of dx prime f of x prime. So that's the only thing affected by it. And then I have 1/2, or 1 over 2 pi times the integral from minus infinity to infinity of the exponential terms, which I'm going to combine. dy. And so what happens is we take this second part here and we define that as a delta function. And so this delta function, basically, if we integrate the delta function from minus infinity to infinity, then what happens is you either get 1 or 0. You get 1 if x is equal to x prime. You get 0 if x is not equal to x prime. And so you can then just say that f of x is just equal to the integral from minus infinity to infinity of dx prime of f of x prime integrated with the delta function. And by doing that, establishing a delta function, you know that this is a circular thing. You could take a function and you could do the Fourier transform of it and then do an inverse transform and know that you're going to recover the same thing back. And it's kind of important that you've got these closed functions with your transforms. Now also what you can do, is everybody cool with this so far? Okay. All right, another thing you can do is if you take the integral from minus infinity to infinity of the f of x magnitude squared. Very similar to what we did before with the adding up the coefficients. Well, this is equal to just the integral from minus infinity to infinity of the complex conjugate of f of x times f of x. And so this is, you can say, is equivalent to the Fourier transforms. So I have dx times 1 over 2 pi of the integral from minus infinity to infinity dy of g complex conjugate of g e to the minus I xy, because we're having the complex conjugate of the exponential term as well. And then you have the other term, which comes from the f of x, where you have, I'm going to call this y prime, g of y prime, and then e I x y prime. And you notice this is not the complex conjugate, so there's no minus on the exponential. Well, you can do the same game here, where you take the terms and you mix them around. And so I'm going to have a 1 over 2 pi I'm going to take out front. And then my integral with respect to y, g complex conjugate of y. And then I have another integral here with respect to y prime. And I have my g of y prime. And then I have an integral involving the dx. So I have 1 over 2 pi dx. And I'm going to take all my exponential terms and I group it here. So y prime minus y x. And what happens is this last term is a delta function. So I end up with 1 over 2 pi times the integral from minus infinity to infinity of the integral of my complex conjugate of g, and then I have my integral of dy prime, g of y prime, and then my delta function. And so what happens is, when I integrate these, this basically says with the delta function that y prime must equal y, right? So now I have 1 over 2 pi of my integral from minus infinity to infinity dy of g complex conjugate of y times g of y, which is the same thing as if I have 1 over 2 pi times the integral from minus infinity to infinity of the magnitude g of y squared dy. So it's kind of interesting because it basically means that I can integrate over time or I could integrate over frequency and I get the same result. So in other words, if you want to know, let's suppose you want to find out how much energy is produced by the sun over its entire lifetime, okay? Then, you know, in time by electromagnetic radiation. Then there's two ways to do it. One is to kind of put a bubble around the sun and measure how much energy is being radiated by the sun and just wait for about 8 billion years until, from the birth of the sun until it dies. Okay? The other is to actually do this, where you just add up all the different frequencies being produced and look at all the frequencies and integrate all these frequencies, and you get the same answer. And so it's just two different ways of doing the exact same thing. Okay. And like I said, this is the best analog to this is to think about like when people move from 45s, you know, the old albums to like MP3s. And, you know, the old music was all analog, which basically meant you had music where you've got a wave pattern that might look like this as people's voice goes up and down and everywhere else. And so you've got a signal that can look like this, which from a storage point of view, if you're trying to store this in a computer, is very difficult because everywhere is different in all of this. You've got all this data going on about what tones are coming out, and you need to record all that information. And what they've done with the MP3 model is basically said, we're going to take this, break it up into different frequencies. And you have this low frequency, which is just a little bit, and you have a higher frequency there's more of, and then this is like kind of in the middle, and then there's a lot of right here, and so on. And you just keep all these frequency bars, and you just store information about how much of each frequency you have at each instant in the music, and you just store up all these amplitudes, and then you just reproduce them. Because you don't need to know, you know what a sine wave is, you know what all the different frequencies are. It's just a matter of how much of each frequency you add together. And by doing that, you can kind of store signals and reproduce them using these Fourier transforms. And then one of the big things is then they developed this technique called fast Fourier transform using computers, where the idea is to be able to calculate these Fourier transforms fast enough so that they're actually useful. Yeah. Everything is 2 to some power, so that you can keep folding and folding it again and folding it again and so on until it works. So anyway, this is the basic idea of Fourier transforms in general, is that you can take a signal, or take it, any kind of signal, whether it's an audio signal or a video signal or whatever, and just break it down into all the component frequencies and look at those component frequencies as opposed to looking at the signal as a whole. And by doing that, you can actually see more of the patterns from a data analysis point of view. You can store your data better. You can do a lot of other things. All right. Next I want to talk about, this is just very brief. Let's suppose you had an even function. Then what happens is g of y is, let's suppose it's equal to, I take my integral for f of x and I break it up into 2 parts. So if f of x e to the minus I xy dx from 0 to infinity, and then I have another part from minus infinity to 0 of f of x e to the minus I xy dx. So this is just one integral broken up into 2 parts. Now, if this happens to be symmetric about x equals 0, then what happens is I can flip the sign, or flip the order of my integration here. So when I flip the integral, so instead of going from minus infinity to 0, I go from 0 to minus infinity, then that flips the sign on x, right? And then I can change my minus infinity to a plus infinity, and that flips the sign again. And so basically I go from dx goes to minus dx and then back to plus dx. And in the exponential, it goes from being, it doesn't change, but then when I flip x to minus x, then that flips the sign here. And now the big question is, what happens to my f of x? If f of x happens to be even, then I do those 2 flips and it comes out the exact same. If it's odd, then I got a problem, and it doesn't work out that way. So what happens is we can write our g of y in this case as being the integral from 0 to infinity of f of x e to the I xy plus e to the minus I xy dx if f of x is even. And this is basically a cosine term, right? So I could just plug that in as my cosine and say that this is an integral f of x cosine of xy dx. If, however, this is odd, and oh, there's a factor of 2 here. If this were odd function of f of x, then at some point I'm changing f of x to minus f of x, right? In which case I would have everything else the same, but I would be changing f of x from positive to negative. There'd be a negative sign in here, and I would end up with something that looks like a sine function instead of a cosine function. So this would be sine xy if f of x is odd. And so what this tells us then is that because f of x is even, and you have a cosine term here which is even, then you're going to end up with a g of y which is even. So in other words, your Fourier transform has the same symmetry as your term. So your Fourier transform has got the same symmetry as whatever the function is you're transforming. So even functions transform into even functions, and odd functions transform into odd functions. And you can have this, we call this a Fourier, a Fourier cosine series. And you also could end up with an inverse transform that looks like this. Where this is g of y cosine xy dy. And like I said, the same thing works for the sine function. And so you can, your symmetry is preserved, which is a good thing. And so this makes our life a little bit simpler if we know the symmetry of our function we're transforming. If we don't, let's say it doesn't have a well-defined symmetry, then you just stick with the exponential terms, just like with the Fourier series. All right. Any other questions so far? I know I'm going through some of this a little bit fast because I figure you guys have seen this a lot before, or everybody should have some exposure to this stuff. If you haven't, let me know if you need me to slow down or anything. But some of the things I'm pointing out are mostly things that are going to be relevant later on as we're getting into other topics like the eigenvalue stuff. All right, so another thing is, let's suppose we had a function, f of t, where it was equal to 0 initially, all the way up until t equals 0. And then at t equals 0, it became a dampened sine wave. So it's minus t over tau sine omega naught t for t greater than 0. Or I could say greater than or equal to, it doesn't matter. So in this case, what happens is your function looks exactly like this, where it's a sine wave, and over time it gets smaller and smaller and smaller. So you have this kind of an exponential envelope on the outside, and inside the sine wave. Dampened harmonic oscillator. So the Fourier transform of this, if this is time, then we'll say this is frequency, is equal to the integral from minus infinity to infinity of f of t e to the minus I omega t dt. We can do this as a sine wave, you know, as a sine Fourier transform, because we do know that this is dominated by a sine wave and it looks anti-symmetric. However, since we're starting at 0, you know, and saying it was 0 on the other side, then it's kind of hard to argue that this is really symmetric, because it's technically, you know, technically there's no symmetry, right? So what happens now is that we use an integral transform. We just simply plug in the function, and the function is 0, so before t equals 0, so we just go from 0 to infinity. That's e to the minus t over tau, and e to the minus I omega t sine omega naught t dt. Okay? And this is the part where all that stuff we talked about last week about integration comes in. Because all you have to do is just integrate that, where, you know, you might take the exponential terms and the sine term and make that into an exponential or whatever. But bottom line, if you integrate everything correctly, you'll end up getting something like this. You have a 1 over omega plus omega naught minus I over tau minus 1 over omega naught, omega minus omega naught minus I over tau. Okay, and so what happens here is that if f of t is, say, the radiated electric field as a function of time, then if you take the magnitude of f of t squared, then that's going to be proportional to the radiated power. And if you integrate that over all time, then that's going to be the total amount of radiated power. So if you take 1 over 2 pi times the integral from minus infinity to infinity, basically add over all frequencies, g of omega squared d omega, that's going to be equal to the integral from 0 to infinity of f of t squared dt. So in other words, you can kind of look at the system and just let it ring out to infinity, and you'll find out how much power was radiated away, or you could just simply add up all these frequencies. That's kind of what I was saying before. And so what happens is each one of these is the same in terms of the frequency at a constant time. But one thing you'll notice here is that you could see a relationship between the dampening, the natural frequency that this thing is ringing with, which is omega naught, and the frequency of the different modes, if you want to think about it, or the Fourier transform frequencies, which is omega. And you'll notice that if omega is equal to omega naught, then you get a huge number here. If omega this term right here, where you have omega plus omega naught, is going to be much smaller than this one. So this term right here is going to basically dominate over the entire function that you're going to get. So what happens is if you plot this, and I'm going to plot the magnitude squared of this guy versus frequency, then it's peaked at omega equals omega naught. And then what happens is you have something that's going to look kind of like this. Now, this term tau that comes in here, the dampening term, that is the thing that keeps you from blowing up. So even if omega is exactly equal to omega naught, this doesn't go to infinity because of this piece right here. And what happens is that relates to the width at half maximum. So 2 over tau gives you the width of that spread. If tau were to go to infinity, this thing would shrink to 0, and you would just have one little spike right there at that frequency. But if tau goes to infinity, what that would mean is that that this thing, the exponential term here would disappear. So we'd end up with just 0. If tau goes to infinity, you'd have exponential of 0, which would give you just 1 here, which means you just have a sine wave. So a pure sine wave would translate into having a Fourier transform, which is just simply a line. And then if you have the dampening term, the more you dampen it out, the wider the distribution of frequencies that you get that can make up that pattern, which means you get this sort of a nice lump here, which is wider. And so it's going to get wider and wider as tau gets larger and larger. Right, other way around. If tau goes to 0. Yeah, because if tau goes to 0, then you can see if tau goes to 0, then this becomes minus infinity, and that means it just dampens out instantly. So you get spread out more then it's less frequencies, then there's more frequencies involved. Sharper means there's less frequencies involved. And so you can also see that as you get near omega equals omega naught, then G of omega approximately becomes equal to minus 1/2 1 over omega minus omega naught minus I over tau. And the magnitude of that is 1/2 1 over square root of omega minus omega naught squared plus 1 over tau squared. And so what happens is you basically can see from here that how this denominator is going to get larger or smaller, but you're always going to be limited by the dampening term. And so if you had a system where you could just sort of eliminate dampening, then you get a real sharp peak in there. And a sharp peak translates, like here, into having a lot of energy just at that one mode. And this sort of comes into like the idea of resonance, you know, and like acoustics, where you take something like a crystal and it has a certain oscillatory frequency, and what happens is if you excite that at exactly the oscillatory frequency, then what happens is it just builds up more and more energy until eventually it breaks, because it keeps generating and generating more energy. This happens like in a microwave oven. When you have microwave ovens are actually tuned to the frequency of water, so that when you pump electromagnetic energy or microwaves into a microwave oven, they're especially tuned to heat up water molecules. And every piece of food you eat has water in it, so it's really heating up the water, and then that water heating up cooks your food internally. So that's why it's good for heating up water. But if you had, say, instead of putting in water, you put in aluminum foil, then there's no resistance actually keeping those electrons from moving back and forth faster and faster, and the little bit of resistance they have heats up the aluminum foil, and next thing you know, you're buying a new microwave. So it's kind of, how it feeds back into itself. So all of these things are just kind of resonance things that happen. And let's see. We can also do Fourier transforms in multiple dimensions, where, let's suppose, instead of just talking about one frequency and one position, we could have, this is the Fourier transform over entire volume. And then you could have an inverse transform, which is similar. And it's a 2 pi is cubed here. And when we do this, you'll notice that k, the wave number, is treated very much like position. And so we can call this frequency space, or k space. And so you can look at your problem in terms, instead of looking at it in terms of what is the position of something, you can look at it as where it fits in phase space. And you can also have your delta function work in the same way. Where this is a 3D delta function, where you actually have to integrate your delta function over a three-dimensional volume in order to get 1 or 0. So it's equal to either 1 in Cartesian coordinates, x equals y equals z equals 0, and it's 0 everywhere else. And so one thing that's kind of neat about this is that, and this relates to quantum mechanics, is that this is the probability distribution of position. Then this is the probability distribution of momentum. And so you can actually see how the two of them are actually going to relate to each other. Because the Fourier transforms, they're, even though one of them is a function of x and the other is a function of k, they actually are related to each other. And let me show you how that falls out. That part's pretty cool. So what we can do is we start off assuming we have a Gaussian distribution of some stuff. So we have a Gaussian probability distribution. And I'm going to simplify this to so we don't have to deal with all these ugly numbers the whole way through. And this is centered at, let's say in spherical coordinates, it's centered right at the origin. And this n is going to be just a normalization constant, so we don't have to keep writing this pi stuff. And so basically, R is equal to the magnitude of X. And what happens here is that A is basically the width of the Gaussian distribution, so that if A gets larger, you got more of a spread, and or it's the other way around. If A gets larger, then you would have a wider distribution, and then if it goes the other way, it's a lesser distribution. So what happens is that we're normalizing this thing in such a way that if you take the magnitude of f of x and you square it and you integrate that over the entire volume, you're going to get 1. That's what we mean by normalized. So if this is f of x, then our Fourier transform is going to be equal to just taking, the integral of this, but we're going to end up having this thing multiplied by e to the minus I k dot x. Okay? Now, when we're doing the integral, we're going to use polar coordinates, and so we're going to set cosine of theta equal to alpha, just to make things a little simple. So I'm going to walk through how to do this integral, because this is one of those things that's kind of neat that you guys should see at least once. All right, so phi of k is equal to 2 pi n times the integral from 0 to infinity of r squared dr, and the integral from minus 1 to plus 1 d alpha of r to the minus e to the minus r squared over a squared e to the minus I k r alpha. Now what's happening is I'm going to skip a few steps just out of time consideration, but you can see here I already integrated with respect to phi because there's no phi terms involved in this. So now I can integrate with respect to alpha really easily because alpha only shows up in this one term, and I have 4 pi over k in integral from 0 to infinity r dr e to the minus r squared over a squared sine of k r. And so now what I did was I integrated with respect to alpha, and so that gave me a minus IKR in the denominator, which I divided through everything. And then I took my exponential term, and I had the positive and negative parts of that, and I made a sine function out of it. And so that's what I end up with right here. So after I had this, I can integrate this from 0 to infinity, and I have this sine function. But what I found is it's easier to deal with this as an exponential. So I take this, and I make it 4 pi over k n over 2I. And if I integrate this from minus infinity to infinity of r dr of e to the minus r squared over a squared e to the I k r, where basically what I did was I decided, well, maybe instead of having my sine term and integrating it from 0 to infinity, I could look at my exponentials as having one going from minus infinity to 0 and another one going from 0 to infinity, and I could just combine it here. So now I have this exponential term where I can just take the entire exponential and I can just put it together into one thing here. So I have an exponential part where I have one part with an r squared, and I have another part with an r term. So what I did, and this is the part that you guys may want to work through in more detail, and I encourage all you guys after class to actually go through this and do this while filling in all the blanks, is I made this part. So it's the exponential of minus 1 over a squared r minus ik a squared over 2 squared. Now this, I guess, requires a little bit of explanation. What I did here was I saw that I had the r squared and the r term here, right? And I could combine that together into the exponential. And I realized that if I added in some extra stuff, particularly a term that involved k squared a squared over 4, then I would have a complete square. And so I did what you guys might remember from algebra class 1,000 years ago, and I completed the square, basically turning this stuff in the exponential into one perfect square of something that I could deal with. And once I had that, then I could do a change of variables. And I could say, well, I have a new variable, which is going to be y equals r minus ik a squared over 2, and then have dy is just equal to dr. And if I do that, then it's going to simplify this entire integral. And the new integral is going to become 2 pi over ik n e to the minus k squared a squared over 4 times the integral from minus infinity to infinity of y plus ik a squared over 2 dy e to the minus y squared over a squared. Okay? And now this interval we can actually solve, because effectively it's just two integrals. One integral is, where you take y times this, and the other integral is just the ik a squared times the dy in this term. And the solution to that, one of those terms, when you integrate from minus infinity to infinity, ends up dropping to 0 because of the symmetry here in the exponential. And so what I ended up getting then was 2 pi over ik n e to the minus k squared a squared over 4, and then the solution of the integral is ik a squared over 2 times a square root of pi. Okay? Then what we do is we just plug back in n equals 2 over pi a squared to the 3/2, or 3/4, sorry. And we end up with phi of k equals 2 pi a squared, 3/4 e to the minus k squared a squared over 4. All right. So that's a lot. And this is one of these little problems that I think you guys can learn a ton from by just doing the Gaussian transform, or the Fourier transform of the Gaussian. Because for one thing, just solving this integral, you learn a lot about how to solve these integrals and how this stuff works and the techniques of dealing with this. And this is exactly the kind of integral you're going to see again and again and again. So being able to work through it and understand how it works is going to be really good for you guys. Another thing you learn from this is just from physics. It basically says that we started out with a Gaussian distribution, and we ended up with a Gaussian distribution. The difference is that one Gaussian had a width of a squared, and the other had a width of, or one of them had a width of a, and the other one had a width of 1 over a. So basically, what that says is that the Fourier transform of a Gaussian is another Gaussian, first off. And secondly, the narrower the distribution of one of them, the broader the distribution is of the other. Okay? So that means that by making, if we had one Gaussian, it was really wide, the other was going to be naturally narrow. And where that comes in handy is that if you think about the delta x is the width of the distribution of, say, the x space one, and delta k is the distribution of the k space, they both basically cancel out the same thing, which is similar to what you see in quantum mechanics, which is delta x, delta p is like the h bar. So in other words, since you're dealing with Gaussian distributions or probability distributions, you get wider in one distribution, then you get narrow in the other, and vice versa, and your overall uncertainty between the two is going to be a constant. So I thought that was kind of the interesting takeaway from this. And you know that you could always end up going from Gaussian to Gaussian. All right, any questions on this stuff so far? But anyway, like I said, I skipped a lot of the math, but because I wanted to kind of run through very generally how that works, and then you guys could actually go through on your own and fill in all the gaps as an exercise. And then as far as the physics goes, this is just an interesting point and just one of the reasons why we use Fourier transforms. And also one thing is that when you take quantum mechanics, you'll notice that one thing this basically says is that quantum mechanics essentially works by Fourier transforms. And the idea that you're kind of transforming things from dealing with them in terms of actual x space to dealing with them in k space a lot. Mm-hmm. Yeah. I mean, yeah, they use that a lot too with the approximation. All right, so last thing I want to talk about are other integral transforms, particularly Laplace transforms. So I titled this whole thing Fourier Transforms, but it may as well have just been integral transforms. And the idea is that Fourier is not the only way that you can transform stuff. Fourier series works particularly if you can claim something is periodic, but sometimes you run into situations where you have something which you know is not periodic. For example, f of x is equal to x squared is not periodic. And to be periodic, what has to happen is it has to have the same solution that repeats, but also the same derivative of the solution has to repeat at some point. So f of x, x squared definitely doesn't fall into that category. And so what they do is they use this Heaviside step function, which is a value of either 0 or 1. For 0 for x less than 0, it's 1 for x greater than 0. In calculating these, so what happens is you end up with this transform, which looks like essentially you take your function and e to the minus c x times a Heaviside step function, e to the minus I xy dx, and your inverse transform. And so what happened, oh, sorry, got ahead of myself. So that ends up, because of the Heaviside step function of 0 for x less than 0, this becomes the integral from 0 to infinity of f of x e to the minus cx e to the minus I xy dx. And then the inverse transform is like f of x e to the minus cx h of x is equal to 1 over 2 pi times the integral from minus infinity to infinity of g of y e to the I xy dy. And so this looks a lot like a Fourier transform in a lot of ways. The only difference is that instead of integrating with respect to just the I xy, you're integrating with the combination of a exponential exponential function and the IY, which we'll call that S. So you can write this as f of S is equal to the integral from 0 to infinity of f of x e to the minus sx dx, and f of x times a Heaviside function is equal to 1 over 2 pi I times the integral over a closed contour of f of s e to the sx ds. And so this is your Laplace transform. And so you can think of this as like a path integral, which we'll talk about next week when we talk about complex numbers. But essentially, this is a different kind of transform, like a Fourier transform. And then in the notes, I'm not going to write it here, but in the notes I talk about other transforms that can be created. And one is a Fourier Bessel transform, where they use Bessel functions as opposed to the exponential term, the e to the I. So it basically takes the place of the sines and cosines with the Bessel function. There's the, and that's also known as a Hankel transform. There's the Mellin transform, where they would use like t to the z minus 1, or t to the z, and transform with that. And then there's a Hilbert transform, which is just something else completely different, where they take the principal part of an integral. So all of these are basically just different integral transforms, and they're closed form transforms. And one of the problems that you're going to see in your homework actually deals with calculating a transform, and actually creating a transform that actually works in a closed form. Okay. All right. So that's it for today. I just don't know if you guys have any questions. And like I said, I know I zipped through some of this, but most of the stuff you guys should have seen before, maybe not at the same level or depth, but it shouldn't be completely foreign. And anything that was sort of the stuff I kind of hand waved with, I want you guys to look over and fill in some of the gaps with. And on Thursday in recitation, we'll be doing more with this stuff.